You can spend time on those Python notebooks, get your algorithms going. There is some data available, and you can use that data for classification. Okay. I will just in the interest of time. Tomorrow I have another 3 hours or so. I'm going to cover reinforcement learning, and then several examples on various topics we cover. Okay, is that a good plan? Or is there anything else you would like to learn, or no? Next couple of days. Okay, yeah, please. Overview of transformers. Yeah, I can do that tomorrow. Transformers, if you're not aware, transformers are used in the large language models. Okay, so that's a very hot topic right now because because of how effective they are in large language models. They use something called attention mechanism, but attention is nothing but correlation. So sometimes, I have a bit of signal processing control background, and I read these computer science papers, and then I think, okay, so these concepts are known, and we've used them in other areas for a long time, but with a different name. So the attention mechanism that's used in transformers is basically correlation at zeroth order correlation. Okay. All right. So yesterday we talked about KNN as an approach to classify data sets. There are many algorithms for classification. You'll find hundreds of these algorithms. It's often difficult to pick one, but there are some that are very popular and have been used in a wide range of applications. KNN is the simplest of all. It's not even there's no optimization, underlying optimization, but there are more sophisticated algorithms that have been shown to be very effective in solving engineering applications. One of those is support vector machines. Support vector machines is a popular classification algorithm. The idea here is to learn a model between input samples and the corresponding labels, which take on C possible class labels. So in other words, you don't have just two classes, but you could have multiple classes, right? So there are 4 different classes here. And the goal is to predict class labels of new input samples. When you're given a new input sample, you want to be able to predict the label of that sample. Support vector machine is, like other classification algorithms, it's a discriminative algorithm, as it finds decision boundaries between classes rather than a model underlying those class distributions. Okay, so we're not trying to find models that approximate the distribution of these data points. Instead, we're trying to find these boundaries between different classes. Okay, I'm going to explain. So I want to use the board. I think it's a bit easier to explain it without the slides. So let's say we have a classification problem where we have 2 data sets in 2 dimensions, x1, x2. I have 1 data set. That's over here. And I have a second data set that's over here. Okay. Now what I would like to do is find a boundary between these 2 data points that separates the 2 classes. Right? Now, how many ways can I find this straight line, this boundary? I mean, it doesn't have to be a straight line, but I'm going to start with support vector machines, linear support vector machine, where we are trying to find a straight line, right? So you can use nonlinear transformations within support vector machine and obtain curved boundary layers. Okay, so that's possible, but for the time being, let's assume that we are interested in finding a straight line that separates these two data sets. How many ways can you do that? Just with a straight line, right? Many options, right? There are infinite ways in which you can draw these straight lines. You can draw many straight lines that separate these two classes. In support vector machines, the idea is to find a straight line that separates these data sets in some optimal fashion. We have these data points. What we want to do, the way we want to find the optimal separation boundary is to find a straight line that maximizes the distance between that separating boundary and the closest data point in each of the classes. Okay. In other words, you want to find this straight line such that the width of this box is maximized. Okay. So why would that be a logical way of finding this straight line? Because when you do that, you are maximizing the separation between the classes, right? That will likely reduce misclassified data points and errors in your model. So that's the idea. So we want this to be the largest possible margin. Yeah, maximize the separation between the two classes. Okay, so that's the intuition, and there's obviously rigorous math behind it. I'm going to go through that quickly. So suppose we have a binary classification task where there are two classes that we're trying to separate. In other words, C, the number of classes, is equal to 2. And those classes have two labels. The label is either -1 or +1. One class is -1, the other class is +1. We model each input, xi, to each output, yi, by multiplying a weight to each input. In other words, we want to find this WT transpose such that when WT transpose, WT is a vector, xi is your feature or the input, and this is also a vector. You multiply those two, that's a scalar. This scalar, if it is positive, then we assign that input xi the label +1. Okay. If this scalar is negative, then we assign that input label -1. Okay. Some points are really large, others are very small, right? So you get a much smoother W when you do this. This is called regularization. It's also used in least squares. So for instance, if I have y equal to ax plus b, right, and I want to solve for least squares, right? So if I want to, so not ax plus b, but ax plus some error, right? Or if you use if we assume it's all scalar, so y equal to some alpha times x plus error, right? If you want this alpha to have nice smooth elements in that vector, okay, so I should probably use alpha transpose here. Then you'll add this term lambda over 2 alpha square to your least squares objective function. Okay. But this regularization term also introduces some bias into the estimate, but it reduces the variance on alpha. Okay, so here, this term, you can use that. You can tune this to reduce the variance in W. Does it make sense, or do you? Yeah. So there are two things that we're trying to accomplish using the support vector machine objective. One is that we're trying to minimize the misclassified data points, and that in order to get the optimal location of the decision boundary. We're also trying to maximize the margins, which is what I mentioned here. We try to maximize this distance, right? That gives you the optimal orientation of the decision boundary, and also the bonus of regularization, which reduces overfitting. So let me zoom in here. It's the same picture that I drew on the board. Okay, so you're trying to maximize this margin so that the separation is as large as possible. Now, one problem with the objective function that I showed you here for support vector machines is that this objective function is not differentiable. Okay. Do you have any background in optimization, gradient descent, Newton-Raphson method? Are you familiar with those? I mean, you may have learned those in the first or the second year undergrad math courses, right? Engineering applications. So I shouldn't say any, but the vast majority of efficient optimization algorithms use some form of gradient descent, right? Which means you have to find the derivative of your objective function. Now, if you take this objective function, this term over here does not have a smooth derivative. It's you can't differentiate that. So to avoid the non-differential kink in the hinge loss, that term over there, it's called hinge loss. We sometimes use a logistic function as a smooth approximation. There are different ways of approximating it. But at the end of the day, if you're using SVM, you're unlikely to formulate any of these objective functions. You will probably use a function in Python. It might give you the option of choosing these various hinge functions, right? It'll give you logistic function, et cetera, and you can pick which one you want to use. So the example that I showed you is for a two-class classification problem. You can, of course, extend support vector machines to multi-class classification problems. So for instance, the way to do that is, there are two ways to do that when you want to extend this algorithm to multiple classes. One is called OVR, or one versus rest, where you take each class, train a binary classifier to determine whether each sample is in class C or not, and then repeat it for all the classes, right? So that's pretty straightforward, but perhaps a bit cumbersome because you have to do it with multiple classes. And for prediction, you test all the models. You will have C different models. For each class, you have a model. You test them all and return the class with the highest likelihood. The other way to do this is it's called one versus one. For each pair of classes, let's say class I and class J, train a binary SVM classifier and repeat it for all classes. And it requires C times C minus 1 over 2 models. Okay, it's a slight improvement over the other approach, one versus rest. So we have multiple classes you have to you have to use one of these approaches for classification. The last algorithm I want to cover under classification is, sorry, this is not the last one. I'm also going to cover random forest. The last couple of algorithms are decision trees and random forests. Have you heard of random forests? Some of you? Yeah? No? Okay. Decision trees. So the idea here, I'm going to take you through an example, and then this will help you understand random forests. So we're going to take this, we'll go through this slowly. So let's say we have some input data X and the corresponding categorical outputs or labels Y. And we want to make predictions Y hat based on what are called binary splits on features Xj. The inputs Xj, the columns in the X matrix are what we call features. Now in this example, this is an example from an yeast production process where you measure temperature, pH, and whether the yield is good or bad. If the temperature is greater than 60 degrees, then you say the yield is bad. If it's not, then you look for pH. If it's greater than 7, then you check if it's less than 9, and then you decide if the yield is bad or good. And if pH is greater than 7, you conclude that the yield is bad. So this is a decision tree, right? So you have to, if you want to classify using decision trees, in this case, the problem is you're producing yeast, and you want to determine, based on the temperature and the pH, if the yield of that process is going to be good or bad, right? And you've come up with this decision tree based on experience. I'm going to talk about how these decision points are created in just a moment. But this is the idea behind decision trees. Every variable has a decision criteria. In this case, temperature greater than 60 degrees, pH greater than 7, and pH, sorry, we lost the power to, okay. pH greater than 7 and pH less than 9, these are the decision points. Okay, so based on these decisions, you decide whether you have good yield or bad yield. Okay, so in this example, sorry, there's a typo here. Y equal to 0 is bad yield. This should be 1. Y equal to 1 is good yield. And then the system has different features: temperature, pH, maybe concentrations of various species, flow rates of various species, bacterial populations, etc., for a grand total of about 60 variables. It can be a very large problem from a decision tree perspective, but we're just going to focus on temperature and pH for now. So individual splits, individual splits that make up the entire tree are called decision stumps. They have a depth of 1, and the splitting rule is based on a threshold value of a particular feature. So whether it's here in this case, it's carbon dioxide concentration, temperature, and pH, and each of these decision stumps are either conclusive or inconclusive. If it's this is conclusive because you know if pH is less than 9, what the yield is going to be, whether it's good or bad. This one is inconclusive because if you go in this direction, then it's conclusive, but if you go in this direction, it's not. So overall, this stump is inconclusive, and the same is true with that one. Right? Now the question is, how do I choose these threshold values? How do I pick these threshold values for each split and for each each feature. So I think the way this is done is we pick different split points and then check the performance of the classifier. Okay, so I'm going to show this by hand. We can do this. Let's okay. So let me put it here. Let me see if okay. If the temperature is greater than some theta, then the yield is bad. Otherwise, it's good. Let's say that's our decision criteria. We need to figure out what theta is. And I've tried different options for theta: 55, 60, 65, and 70. Okay. If the temperature is greater than 70 degrees, if that is your rule, split rule, then the classifier has an accuracy of 5/8. Do you see that? I'll give you a moment to think about it. So if the temperature, your rule says, if the temperature is greater than 70 degrees, then the yield is bad. Okay, so let's say you go with that rule, then how many of those, is that seven data points, would you get your conclusion right? Sorry, yeah. Yeah, so can you explain that? Yes. Do you want to use the microphone? I think.
If temperature is greater than 70 degrees, so this split rule, as per this split rule, the yield has to be bad.
Right.
But there are other data points also where when it is 65 and when it is 50, that also is still bad.
Right.
So that is not accounted for in this particular split rule.
Right.
So out of those 6 bad yield data points, there are only 5 are accounted for. How many? 1, 2, 3. It is 4 out of 8, sir, I guess. Maybe I need to check once again.
See, you're going to be correct. Okay, so let's do it step by step. I'm not going to copy the entire table here. So let's assume this is your split rule. Okay. If that's your split rule, do you get the first one correct?
Yes.
Right. The first one you'll get it correct because your temperature is 85, it's greater than 70. Your classifier will say yield is going to be bad, and that's in fact bad. Right? You'll get it correct. So what about the second one? It's correct, right? The third one?
Yes.
Correct. Okay. So the fourth one?
It is at the boundary, so it may take.
I mean, it's not quite at the boundary because it clearly says it's temperature greater than 70. So if it's not greater than or equal to 70, right?
Okay.
So it's greater than 70. So do you get the fourth one correct? No, right? So your classifier will say it's good. So this is wrong. And fifth one, what about fifth one? Sorry, yeah. It'll get it right? That's 65 degrees, right?
It shows it as good.
65 is the fifth one from the top.
It's
wrong,
wrong,
right? So
wrong.
this is also wrong. And what about the sixth one? Sorry? Yeah. Sixth one, is it correct or wrong? Right? Yeah, it's right because the sixth, this is good, right? The batch is good, and your classifier will check the temperature. It's less than 70, and therefore it will conclude it's good. Right? So the sixth one, you're going to get it right. What about the seventh one? That's also right, right? What about the eighth one? This is wrong, right? So out of 8 samples, you are only getting 5 correct with this split rule, right? So therefore, the accuracy of this classifier is 5/8. Now you can go through the same exercise and find the accuracy of different split rules for this particular data set. Okay. So given all of these, which split rule would you pick for your classifier? Sorry? Yeah. The third one, right? Yeah, temperature greater than 60 degrees. So that's now this, we are able to do this easily because you just have one feature. It's low dimensional. You don't have, you don't have too many features there. But if you have lots of features, this exercise can be quite cumbersome. So, for instance, if we have D features, how many splits do we need to perform in total? Potentially 2 to the power of D splits, which is a really large number if D is large. Right? So if you have lots of features, you'll have to do 2 power D splits, and that's not easy. Right? So, sorry?
These are the quality parameters for the crop. So do we have the freedom to choose the temperature and all for the classification?
Do we have the freedom to choose in the experiment? In the model, yeah.
Yeah, in the model, do we have freedom? Because in reality, it might be the crop might be good for only particular temperature.
Uh-huh.
So can we consider different temperature ranges for our classification?
Oh, I see.
To
Okay.
enhance
So,
it.
so in this case, somebody did these experiments at different temperatures because they're trying to figure out what's the optimal temperature, right? So, yeah, I would say in this case at least we could choose different temperatures. I'm not sure if I answered your question. Is that your question? Did I answer your question?
Means I want to ask that for the crop, the good or bad yield will be at particular temperature only. Means for particular temperature, after that it will be good or bad.
Mm-hmm.
But for classification, we are trying different temperature ranges to get better accuracy. So
Right.
means it's actually possible.
Right. Right. Yeah. I think that's right. Yeah. 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 Uh-huh. Uh-huh. This is an iterative process. You have to, there's a bit of a trial and error involved. And I'm going to, because decision trees are computationally very expensive, there's a lot of trial and error involved, right? That's why we use random forests that reduces some of this complexity. Let me go through random forests and then you'll get a better feel for this. Okay. So if you have D features, then you'll potentially need 2 to the power of D splits, okay, or more, which can be a really large number. So let's say you have 100 features, then it's 2 power 100. That's a lot of splits that you have to tune, and that's obviously not computationally easy. So we use what are called random forests, where the idea is instead of using all D features, we use a randomly selected subset of those features. Okay, so we don't use all of those features, but just a randomly selected subset of those features. And similarly, instead of using all the samples, we use a randomly selected, uniformly sampled subset of the original data set with replacement. This is called bootstrapping. I have an example, so as we go through that, you'll understand this better. Okay, so there are 2 things we're trying to do to reduce the complexity, computational complexity of the decision trees, right? So we're trying to, instead of using all the features, in the data. We randomly select a subset of the features. And instead of using all the samples, we randomly select a subset of those samples with replacement. Do you know what with replacement means? Selection with replacement. So if you have, so let's say your data, you have 100 data points, x1 to x100. You're randomly sampling from it. Say you decide to take 10, so your first sample could be x2, and then you put x2 back into your set. You're not removing it. So it's possible that the next time again you'll pick x2 because it's back in your set, right? So that's what is meant by with replacement. We select random samples from the data with replacement. And then we repeat, we perform many repetitions of steps 1 and 2 and take the majority vote in terms of results, which is called aggregating. So I'll explain this in just a moment with an example. So the combination of bootstrapping and aggregating, it's called bootstrap aggregating or bagging in literature. Okay, here's the example. So in this case, we have 100,000 samples. And if we randomly and uniformly sample from our existing samples with replacement, our samples could look like this: x1, x101, 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 because you're replacing it. So there's a small possibility that you'll pick the same sample again. Okay, so that's with replacement. You generate your samples. And this single experiment or iteration is known as bootstrap sample. Okay. So suppose we took out of the 100,000 data points about 10,000 bootstrapped random samples, or also called forests. Now we want to pass the original X through each model and record predicted labels. Okay, so we sort of make a tally. So random forest 1, the predicted output, you get a certain predicted output. Random forest 2, you get a predicted output, and so on. Then you have predicted outputs for each of these 10,000 samples. Okay. We then take the mode or the majority vote across all of these results. This becomes our final predicted output. Okay. So this visualization, this picture really explains how this is done. So you have 10,000 different bootstrapped models. With each model, you have a decision tree, and those decision trees will tell you for a new data set whether whether the data belongs to 0 class or 1 class, right? So each of these models will give you an answer. Then the output of the random forest is the majority vote. Okay, so each model will, so in this case you have 3 models, the majority vote is 1, and therefore the prediction from the random forest is 1. Now, naturally, you would think that if there are large feature subsets or more iterations, they lead to better performance. Okay, so if you have more forests, more features in each of those forests, then you get better performance. Is empirically one of the better performing models if domain knowledge is scarce. Random forests are widely used. In fact, in our experiments, we found random forests to be much better than a variety of other classifiers. For some reason, in a wide range of industrial applications, we found that random forest classifiers are far better than other classifiers. And because you're not dealing with all the features, you're dealing with a subset of those features, and you're also dealing with a subset of the samples in each of those forests. It's much faster, computationally faster. Okay. Okay, so, and then I'm going to talk about clustering algorithms. I want to pause here and get you to code in Python a couple of clustering algorithms. Is that okay? Yeah. So if you go back to the same Dropbox folder, there's a second folder. I think it's called S2 that it's labeled clustering and classification, I believe. Sorry, it's called classification. Sorry, not clustering, just classification. You can open that Python notebook. I would like to do a couple of things. The data are already there, so please use the data from the Excel spreadsheet. The notebook takes you through all the steps that you have to go through to classify data. I don't believe it shows you how to do neural networks, so I want you to add a neural network classifier to that data set. Okay, so I'll give you half an hour to do that. I'll walk around and help you. everyone done with that file? Sorry? You're doing it right now. If you're done with what's in that code, I would like you to converse with Gemini and build a neural network classifier. So the code does not show you how to build a neural network classifier. As I mentioned earlier, um, almost all supervised and unsupervised learning problems can be solved using neural networks. Right? So you can now use a deep neural network classifier on the same data and check how it performs. Does it perform better or worse? You can also try a logistic classifier, logistic regression classifier. But let's try deep neural network. Yeah, with deep neural network. finish your own network, what you can do is you can plot a bar chart showing the performance of different algorithms, the accuracy of. If you're done, we can discuss clustering. Do you need more time? Anybody needs more time? You're done? But those on this side, are you done? No? You need a little bit more time? Okay, so why don't you take 5 more minutes? I think we have to finish this at 11:30, so 5 more minutes, and then let me see if I can help. Neural network. Which algorithm? I mean, you get a hang of it, right? Did anyone try neural networks? Deep neural networks? Did it work? Do you get better performance, or is the performance really high with all the algorithms? Do you want to show what you did? Sorry? Yeah, okay. Do you want to do mind? You have HDMI. HDMI. All right. Okay. Can you keep it here?
So these are the plots I got for SVM, random forest with no bootstrapping, random forest with bootstrapping, and neural network. So the accuracy of this blue one is training accuracy, and the red one is testing accuracy. So right now I'm getting better performance for random forest, almost similar performance for no bootstrapping and bootstrapping, but the neural network performance we can tune and we can make it better than neural for neural network. So there are scope for improvement. I didn't try that thing, but we can try that thing also. So these are simple neural network. Sir, this is the like 10 six simple neural networks. मतलब TensorFlow में they have implemented, but we can like standard neural network. Only standard neural network. We have used ReLU and softmax in the end. So these are the tuning parameters. We can change this ReLU, softmax, number of layers, number of nodes. So these will be the tuning parameters. So you can modify the performance of neural network. So this is the advantage of neural network here over previous stated methods like random forest and SVM and these things. And oh, we it's not we can't say these things if we can't implement, because these things, it's not necessary if we increase the layer then the performance will increase. There sir has told the problem of overfitting and underfitting, so like those kinds of problems are also there. There is method of drop dropping the layers. We drop the layers so to avoid redundancy. So sometimes more number of layers can also be a problem. So we have to optimize it. So we can do those things are tuning parameters. You just tune it and check it. Okay.
Thank you. Appreciate that. So I think one lesson from the graph that we had seen just now is that there's no guarantee that if you use this one of these complex models that you'll get better performance. Right? On top of it, there are a number of hyperparameters that you have to tune, and the ultimate performance depends on what hyperparameters you choose and how you tune them. So there are a number of things that eventually determine the quality of the classification model. And you want to be conscious of that. Often this ends up being a bit of a trial and error exercise. When you solve these problems many times, you'll have some intuition, and given a certain problem, you'll then be able to decide which algorithm you want to use to solve classification problems. Now, that sort of brings us to the end of classification. Now, I want to ask you, do you have a good understanding of how to identify a classification problem, and then how to formulate it, and how to solve it using Python? Right? So that's really what I'm hoping are the takeaways from this exercise. All right, so in the next 15 minutes or so, I want to quickly introduce you to a clustering algorithm. It's called the k-means algorithm. It's an unsupervised clustering algorithm. Clustering, as you know, is an unsupervised machine learning process. It means it simply analyzes the existing data. We use the existing data, and we don't have class labels for new samples. So just like KNN, K nearest neighbors algorithm, in classification, we have what is called k-means algorithm for clustering, where k is a parameter that you choose. K determines the number of clusters you want to form from the data. And it's a very popular off-the-shelf machine learning algorithm, and is available in a wide range of software tools. Does anyone here use Julia? Have you heard of a software called Julia? It is, you have tried it? Have you tried it? Yeah. Right, yeah. It's supposed to be much faster than Python. There are groups that use Python primarily, especially when they need algorithms to run faster, or if they're computationally very complex and need faster code, they use Julia. Okay, now here's a quick description of the k-means algorithm, so that will slow down the algorithm. Now, after you identify the k nodes, these are called the mean nodes, you assign the remaining samples to one of the k nodes. Okay, so you pick your k nodes. I have a picture in the next slide I'll show you in just a moment, but you pick your k nodes, you assign every data point to one of these mean nodes. Okay, so in other words, so let's say these are the two clusters. So you pick one data point here, one data point here, you measure the distance of every data point, and you assign those data points to either this cluster or this cluster. Okay. So if a data point is closer to this point, then you assign it to this cluster. If it's closer to this point, you assign it to this cluster. So you do that with k nodes. Now, once you do this, what you will once you find these two clusters, obviously these are not the right clusters, right? So you have some overlap between the two clusters. You find the new mean of this cluster. You find the new mean of this cluster, and then repeat this process. Reassign all the data points to one cluster or the other. You keep repeating this until you have some sort of convergence. Okay. So here's a picture that explains Okay, I'm trying to remember why. I think there are three clusters here or four. I see 1, 2, 3, right? So you see only 3 or 4? 3, right? Yeah. So in the first iteration, everything is in the same cluster. I mean, you don't have clusters, right? So that's why all the data points are shown in black. There are no, you don't yet have clusters, but you picked you picked three data points, and you call them 3 different clusters. So one is a red cluster, a green cluster, and a blue cluster. Okay. So when you pick those data points, all other data points have not yet been assigned to any cluster, so they are all black. Okay. And then you measure the distance of each of those data points from the 3 means that you've started with. Okay? And all the data points that are closer to the pink one, you assign them to the pink cluster. Then you have this dark blue cluster, and then the light blue cluster. So the data points are assigned to one of these clusters based on to which cluster those data points are closer. Right? So these are the means. If all the blue points are closer to this mean, all the pink points are closer to this mean, and the light blue ones are closer to this mean. Okay? And then once you do that, once you have these data points, you re-estimate the means of each of these clusters. This cluster has a mean, this cluster has a mean, and that one has a mean. Right? And that's not going to be the old mean. You have added more data points to the cluster, therefore your mean changes. Now, if you look at this cluster, it's very easy to see. You have 1 data point here and 5 over there. Obviously, the mean must be somewhere over there, right? Not here. So when you take those data points and recalculate the mean, it shifts there. Okay, so it's going to be over there. Similarly, the mean of blue, it's here, but it shifts there. This one, the mean shifts a little closer to the data points at the top. Okay. Now you repeat that process multiple times. You keep repeating it until you get a clear separation of these clusters. So that's the k-means algorithm. It's a very, very straightforward algorithm. All right. Any questions on that? Sorry, do you have a question? In the second image, we have 4, or we have only 3, right? Right.
But the data is different variants.
Right, right, yeah.
So we'll take the mean of that particular
Right,
data set.
right,
If there is much biases shows or variance of the data is there, so we'll take that particular mean of that data.
right.
So because there is we see in the 4th image, so there blue or data is still much varied. So
This one?
last one, the dark blue data set.
This one? Yeah,
Yes, yes, yes.
yeah,
But in the 5th one image, we see that the pink and blue one data set are closely each other,
right,
right? So we'll take the mean of that particular data set.
right,
What we have.
right,
It will be separated.
right. Yeah, it'll slowly separate. I mean, you can see it. You start with all black data points, right? And then here, because you've randomly chosen the 3 means initially, there's obviously misclassification or misidentification of these clusters. If you observe the pink cluster over there at the top, ideally those data points and these blue data points should be in the same cluster, right? But because you've started in your initial means are randomly chosen, you end up clustering those pink ones with these pink ones instead of clustering them with the blue data points here. That would be natural, right? Okay. But through the algorithm, because you continuously shift your means, so you see here again you have these pink ones are classified with these pink ones. And then as these means are moving, so now in this case, for instance, in the next iteration, what happens is these pink data points are closer to this mean than to this mean, right? And therefore, in the next iteration, you're going to classify that you're going to say these data points belong to this cluster, not to this cluster, okay? Which is exactly what happens here. So the color of these data points changes. You now have those data points belonging to the light blue cluster, right? And the iterations continue, and eventually you have much better separation. Now this depends a lot on how you choose K. If you choose, for this data set, for instance, you could have chosen only 2 Ks, or 2 means, right? In that case, you would probably cluster these into one group and these into another group, right? Or you could have chosen 5, and then it'll divide this data into more clusters. Mm-hmm. Yeah, so I think I have model accuracy. Wait. Sorry, yeah. I mean, not right. I mean, it's hard to tell because you don't know. So let's say in 2 dimensions, it's easy to see, right? In very high dimensions, let's say you have 100 dimensions and 5 different classes, right? Or how do you tell? It's not easy, right? Right. Yeah. Right. 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 I mean, if you have intuition, it helps certainly. But if you don't have intuition, I guess his question is, how do you compare a cluster with, a data set with 2 clusters versus a data set with 3 or 4 or 5 clusters, right? I mean, in the extreme, you can have as many clusters as the data points. That's not, that's. I think typically it depends on the application. Where do you want to use? How do you want to use? And you can also use the size of these clusters as a measure, right? So, for instance, if you only use 2 clusters, the size of this cluster is really big, right? Is that something that is desirable, or do you want a cluster that is much sharper, is smaller, right? So you can perhaps use the size of these clusters as a measure of how good. So if you do 2 clusters, then you'll find that these clusters, one cluster is really large compared to the other one, right? So then you might want to increase the number of clusters so that all clusters are uniform in terms of their size. Okay. There are different ways of finding size. You can look at the volume of these clusters, or the distance, the largest distance between the data points and the cluster. You can use different measures. All right. Is it 11:30? I think we are supposed to stop it. Yeah. So we'll take a quick break, 15-minute break. We'll reconvene, and then I'll take you through a dimensionality reduction algorithm. Thank you. Hi. Okay. 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 Yeah. Yeah. Sure. Yeah. Right. Right. I think GPA is very important. The GPA.